All right, here we're back one last time to talk about momentum in chapter 5. We're almost done. We should finish up this time. That's the good news. All right, first thing is let's talk about the momentum. Let's look at the example of a cannon up here. If you have a cannon with a cannonball inside, okay, we know the formula for momentum is mass times velocity. Okay. Now, in this case, technically, we have two momentums. All right. To get the total momentum, we'd have to take the momentum of the cannonball plus the momentum of the cannon. All right. And we would say that constitutes the system. Just like down here, we have a cannon and a cannonball, and that's the system. Anything that's outside of the system that acts on it, besides the cannon and the cannonball, would be considered external. Okay. Anything in the system would be the cannon and the cannonball. All right. Now, in this first one, the velocity of the cannonball, which would be in here somewhere, we can't see it because it's in there, the velocity would be 0 because it's not going anywhere. So 0 times the mass of the cannonball, whatever that would be, is going to be 0. So the mass of the cannonball is, the momentum of the cannonball is 0. The mass of the cannon would be a lot bigger number, but the velocity of the cannon, when it's just sitting there, is also 0. So 0 times the mass of the cannon is equal to 0. So we would say that the net momentum, okay, or the total, if you put them all together, the net momentum, so I'm going to use the P for momentum, okay, is equal to 0. Now, if we fire the cannon, we're still talking about the cannon and the cannonball, no other things hitting the cannon or anything else exerting a force on the cannonball. All right. What would be the momentum now? All right. Well, let's just say that the cannon has a mass of 200 kilograms, and let's just say that the cannonball has a mass of 2 kilograms. All right. And so this would be it. Now, to find the momentum, we would have to take the mass of the cannon. So let's just say 200 times the speed of the cannon. Let's just say that it goes back at 5 meters per second. That's really fast, actually. Let's make it 0.5 meters per second. Okay, so it's going back at 0.5 meters per second. If we multiply that, 0.5 times that, it's going to give us 100 kilograms times meters. Dot just means times per second. Okay. Now, the cannonball is going in the opposite direction. So when we add these together, we'd be adding plus a negative, because the cannonball has momentum, and it's a vector quantity, so it has direction, and it's in the opposite direction, so it could be negative. Now, technically, it doesn't matter which side is negative, which side is positive. We could very well have made this negative, because it's going to the left, and this one's going to the right, positive. But the point is, they're the opposite. So basically, they're going to subtract from each other. All right, and let's say that the cannonball still has a mass of 2 kilograms, and it's going to be times its velocity. So it turns out its velocity is going to be 50 meters per second. Well, 2 times 50 is going to give you 100, so it's minus 2, so it's going to be plus negative 100 kilograms times meters per second. I'm not going to write that out because I'm trying to do this with my mouse pad. But yeah, so if we have 100 plus a negative 100, what are we going to end up with? 0 momentum, basically. Kilograms times meters per second. Okay, and so the net momentum before and the net momentum after are the same. And so we would say that the momentum is conserved. In other words, we have the same amount as we did before. The net total, okay, is still the same. Okay, it was 0 up here. Now we have momentum of the cannon moving this direction, the ball moving this direction, but since they're in opposite directions and there are equal amounts of momentum in each direction, they cancel out and come back to 0. Okay, so as long as there's no outside forces coming in and affecting the cannonball or the cannon, the momentum should be conserved. That's what we talk about. All right. Before we go on, let's talk about a couple other things here. Which receives more force, the cannonball, or is there greater force acting on the cannon? Think about that. The correct answer is they're the same because we have action-reaction force. The gunpowder exerts a force on the cannonball, but there's also a force exerted on the cannon. And so the force is equal. Now, the result of it is not the same. So if I asked you which one had more momentum, which one has more momentum, the cannonball or the cannon? Well, we figured out both of them have 100 kilograms per meter per second, just in opposite directions. So neither one of them has more momentum. They would have the same change in momentum and the same momentum. All right. Because even though the cannonball is going a lot faster, it has a higher velocity, it has a lower mass. And same thing with the cannon, it has the opposite. It has the higher mass, but it has a lower velocity. So the change in momentum is going to be the same for both of them. All right. And so that's something very important to keep in mind. Another example would be if you have a little bug and you have a big old truck. I'm just going to draw a big square truck. Or bus, if you want, it looks more like a bus, okay? When this bus runs into the bug, which is going this direction, which one exerts more force on the other? And the correct answer is 0, okay? They're exactly the same. Neither one of them has more force than the other. Newton's law, every action has equal opposite reaction. They exert the same amount of force on each other. Now, the change in acceleration is going to be a lot greater on the bug. And always it's going to be slowed down to 0 and basically sent back the other direction so fast that a head basically bounces out its rear end. But it's not going to have much effect on the acceleration of the bus. Technically, it would go a little bit slower, but not even enough probably to be noticeable. All right, just like down here when we shot the cannonball out, the acceleration of the cannonball is going to be a lot higher than the cannon because it has less mass, and so having the same force on it is going to make it accelerate faster, whereas the cannon has a lot more mass and it's going to accelerate less. But the force on each one is exactly the same. Okay. The last thing that we're going to talk about is momentum in collisions. Okay, when one object runs into another object and collides, there's going to be momentum involved. Both objects have momentum before, and they're going to have momentum afterwards. All right. If two objects, let me get my drag thing down. That's not my mark. All right, if we have two objects that are going to hit each other, okay, for example, here we have two balls. The yellow one, I believe it is, my colorblind, is going to be hit by the green one. The green one's moving, so it has a certain momentum. The yellow one has a momentum of 0. Okay, after the green one hits it, there's a collision. Then in this case, the green one is now stopped, so its momentum is 0, and the momentum of the yellow ball would be a positive number now because it's moving, and it's moving in the same direction the green one was. All right, and what speed is it moving at? Well, if momentum is conserved, we know that now the yellow ball is moving at the same speed as the green ball was moving before it hit it. All right, all right. In this case, we have a green and yellow ball. Both of them are moving. They're moving in opposite directions. If they're going at the same speed, their momentum would be 0. They hit, and they reverse directions. All right, this one begins to go to the right. This one goes back to the left. And since they're going at equal speeds, they would once again still have a momentum of 0 if they were going at the same speed. Okay. In the last one, in this case, they're going both the same direction, but the one behind it, the green ball, is going faster, and so it's going to hit the one before it, and when it hits it, it slows it down a little bit, but it makes the other one go faster again. Okay. All of these are considered elastic collisions. They come and they bounce apart. Ideally, in a elastic collision, it's when the object is not permanently deformed and it does not generate heat. We say, in other words, it bounces perfectly. They hit each other and bounce apart perfectly. Okay, that is considered an elastic. They bounce apart, they hit, they're not crunched up by it, so that is considered to be an elastic collision. Now, on the other hand, say we have these two train cars, and one is moving, the other one sits still. When this one runs into that one, they hook together. That's basically how they hook the cars together. They just kind of slam them together, it locks together. Okay, now they are hooked together. This is considered an inelastic because now they are connected. In inelastic collisions, they either stick together or, as in the example up here, where you have collisions, they are permanently deformed, scrunched, and very often hooked together. If it's perfectly inelastic, they would actually be hooked together, okay, and remain hooked together. Now, in real life, if two objects collide, can they do that without generating heat? And the correct answer is no, they cannot do that. There's always going to be friction when they hit, and it's going to generate heat. And so there are no perfectly elastic collisions in nature for the most part. Now, on the atomic level, atoms have electrons, which are negative on the outside layer, and they repel each other. And so atoms will actually repel each other and do have almost perfectly elastic collisions, okay? But for things bigger than that, no. Usually there's going to be some heat generated and friction and so forth, okay? And many things will collide and they will not hook together. They may kind of hit, but then they come apart. So most things are not perfectly inelastic either, okay? They're more likely to be perfectly inelastic than perfectly elastic, but they're actually somewhere in between there, okay? Now, when we look at these collisions here, for example, notice there's once again a conservation of momentum. These are the same mass and they're going at the same speed. Since they're going in opposite directions, we would subtract them, so their net momentum would be 0. When they hit into each other, they hook together, they're permanently deformed, so it's inelastic, perfectly inelastic, and their momentum now, because they're not moving, is also 0. So it's kind of the reverse of the cannon, where they're still at the beginning and they're moving at the end, but they still cancel out. Here they cancel out, but at the end they're not moving, so they still have a net momentum of 0. Okay, same thing here. We have the truck rams the other one from behind, but they stay hooked together, so that makes it a inelastic collision. But the momentum here, if you add the speed times velocity, or mass times velocity here, plus the mass velocity here, and you add the mass of the two together plus their velocity, you would find that you have the same amount of momentum. So momentum is still conserved. So anytime you have a collision, momentum will always be conserved. It doesn't matter if it's elastic, where they bounce perfectly apart, or if it's inelastic, where they are deformed and they stay hooked together. Either way, momentum is always conserved. And that about wraps it up for momentum. We'll probably have some problems to practice on and stuff like that, but we'll talk more about that and some demos and stuff when we meet in class.